So, how do we compare the cost competitiveness of different energy storage technologies? One way is to use the levelized cost of electricity. And so, we talked about this a bit before in the context of wind and solar. And what this refers to, again, is sort of the lifetime cost, operational cost, but also capital cost of a technology divided by the amount of electricity that produces over its lifetime. So, obviously, when we talk about the levelized cost of electricity for grid scale energy storage, the electricity that it's producing is actually electricity that it's discharging that was originally purchased from a wholesale electricity market or another generator and stored in the energy storage device first. And so this figure gives you a sense for the levelized cost of electricity for different batteries. On the x-axis, we have dollars per megawatt hour. And then we have different energy storage devices and also different uses. And the different uses mostly influence the capital cost or the unit cost of the batteries. In general, when we talk about in front of the meter, that would be utility scale devices. So batteries that are sort of interacting on the wholesale market with wind farms or solar farms. When we talk about behind the meter, those are batteries that are being placed at individual people's houses. And so what this also compares is the levelized cost of electricity for essentially in front of the meter or grid scale energy storage with the most expensive type of electricity that we typically have in the grid, which would be peaking oil generators. Those would be diesel oil generators that might be used as backup at hospitals or other critical infrastructure. And so what you see is that the levelized cost of electricity for grid scale, sort of utility scale energy storage technology is already cost competitive with the most expensive peaking devices that we're using today. So what that means from an economic standpoint is that grid scale energy storage is already cost competitive in a kind of a limited sense, right? If we think about the system supply curve in an electricity market, the most expensive power plants that are on the grid are all the way at the top right. Those are sort of backup generators that we only use in an emergency, right? Because they're otherwise too expensive. And so batteries are already there, right? So we could conceivably start to replace those really expensive power plants all the way at the top right with batteries. But as the cost of batteries declines, they will become more and more competitive in an economic sense with a broader swath of generation technologies that we see in the system supply curve. So you could think about as the cost of batteries declines, they start to fall along this system supply curve and potentially could start to replace more and more types of different generation. So already in some systems, New York and California batteries are starting to replace the most expensive peaking power plants that we have. And future price declines look inevitable. And so what I'm showing here is it's older information. It's about 5 years old. But what it does do a nice job of is giving you some perspective. The green data is actually tracking the falling cost of solar, which we've talked about. One of the most transformative changes in the electric power industry over the last several years has been the falling cost of solar. And what it looks like, at least initially, is that the cost of batteries is declining at about the same rate. The other thing that I'll note, we've been very focused on the electric power industry this class, and that won't really change until the very end of the course when we're going to broaden our perspective a little bit. But I do want to note that if we're talking about decreasing carbon emissions broadly across different economic sectors, one of the most difficult areas to decrease carbon emissions in is the transportation sector. And there the goal, of course, is to substitute in cleaner, low carbon transportation technologies for our current reliance on internal combustion engines powered by gasoline. And so the batteries, the price of batteries as they decline, poses significant potential benefits in terms of our ability to cost effectively replace internal combustion engine cars with hybrids and electric vehicles. So this shows similar data that depicts the falling cost of batteries on a dollar per kilowatt hour basis. We see two falling trends here. So gray is sort of the market average in terms of battery prices, and red actually shows the what you could argue would be the market leader in batteries, which would be Tesla and Panasonic. And we're also comparing those prices as they decline to two sort of thresholds. The first in purple shows the battery prices that would be required to produce affordable electric vehicles, and green would be the battery prices required to produce economy electric vehicles. And so what I assume economy means is they would basically be able to replace the cheapest internal combustion engine cars on the market. And what this suggests is that we're really not far away, maybe 4 or 5 years away, from potentially having batteries cheap enough so that we can mass produce very affordable electric vehicles. So, as I mentioned before, this could be critical to tackling greenhouse gas emissions in the transportation sector.